I am going to talk about over the last several years. So I have been in part of building large scale distributed systems at Target. So today for the next 20 to 25 minutes, I am going to talk about how we bring in the agility, stability and scalability while building our services at Target. I am sure many of you know about Target and heard about Target. So I am just quickly going through a refresher on who we are. As we all know, Target is one of the largest retailers in US. So we have close to 2000 plus stores running across US for the guests to come and shop with us. We are multi-category retailer where we provide apparels, groceries, patios, furnitures, electronics, etc. Our digital presence is going very strong over the last few years. We provide a lot of services to the guest. For name to few of them like drive up, pick up, where we allow the guest to kind of order the items online, and then they can go to the nearby stores, and then someone at the parking lot will be available for them to just hand over the item to the guest. We also provide services like same day delivery, where guests can place an order online, and then within few hours we could deliver them at their doorsteps. So Target has been growing from the business perspective over the last few years phenomenally. We have grown from a $70 billion company to an $110 billion company. Checkout platform makes a crucial as part of this business growth. So before we get into the topic, I just want to give a quick snapshot around how our commerce platform is deployed in production as of today. We have close to 2000 plus stores, and our commerce services are running across all these stores as a mini cloud services. Our digital presence is provided through Google Cloud Provider, and at given point in time, our commerce services are running in close to 1000 plus containers in the Google GCP. Our applications are able to scale close to 500,000 orders per hour volume. We are able to meet our latencies of our APIs under 150 milliseconds. Lot of times our services are hit hard by guests or bots in a given point in time, and we have seen as close as 150k order all TPS getting used by our services. Lastly, over the last few months, we haven't seen any incidents related to our commerce service. These numbers looks magical, isn't it? For a large scale enterprise like Target, these numbers are phenomenal. How exactly we achieve these numbers? At Target Tech, we have these 4 key pillars, which I am going to talk about each one of them in details. Product engineering, performance engineering, site reliability engineering, and lastly platform engineering. So let's talk about the product engineering. The primary goal of a product engineering at Target is to ensure that we bring in the agility to the business. So how exactly we do that in Target? Like any other enterprises, Target was also in a monolithic path for a very long time. So we had 2 different set of systems catering to our business needs. We had one for stores and one for digital. And stores legacy systems were so complex, even a small change, you need the legacy knowledge. Over a period of time, we started seeing ourselves drifting away from the functionality between these channels, and we caused inconsistency to our guest behaviors. Now, like any other enterprises, we also started moving into the modernization path. As part of that, we choose a monolithic application architecture pattern to achieve the same. We all know that monolithic microservice architecture pattern helps us bring down these entire monolithic services into some smaller subsystems. Each one of these subsystems can able to build, deploy and scale independently. while we trying to adapt the microservice API for core commerce or the commerce services, we thought about how exactly we can bring in some commonality between the stores and the digital capabilities. Let's look at it what I mean by that. If a guest do and let's say an add to cart in digital, or if the guest do and goes to the stores and scan an item in the checkout self-checkout aisle, you pretty much see these core functions getting executed at both these places. We look for items, we look for prices, and then we also see if there are any discounts associated to this price, and then we ask for the guest to pay through any of these payment methods. And once all this done, guest will do the checkout. Now, if you really look at it, most of these capabilities between the digital and stores are common, except that there are few places like digital we don't allow, let's say, a cash as a tender. Now, how exactly using microservice architecture we can bring in this commonality? So we started adapting a principle called platform tenant architecture principle. So it looks really a buzzword. What exactly it means? So as part of the platform component, what we decided to do is whatever the core common basic functionality for a capability, we started providing them as a platform component. These platform components are nothing but a set of core microservice APIs, and it provides these capability for any of the channels to leverage them. We don't have to have any channel specific implementations over these layers. These components or the platform components which we call is available at the enterprise level so that anybody can use these services for their need. And also, given that these services are provided at enterprise level, we wanted to maintain the stability of these services because these are the core fundamental building block for any capabilities. Now, once we build these core capability, how do we leverage them in the individual channels? Now, as part of that, we call them as a tenant layer. So with the tenant layer, what happens is that business requirements specific to a particular channel can be customized by using our platform components. So they use our platform components, which are nothing but the microservice APIs. And then whatever customization they want to bring in to that particular channel, they'll go ahead and adapt them in the tenant layer. So this way, we could kind of separate the two key things, stability and the agility. The platform provides a core capability which brings in that stability for our business, while in the tenant layer, we kind of build in that agility where the guest business requirements can be plugged into that real quickly, and then we should be able to go ahead and test it quickly. So this way, we could bring in some of the agility to our business from the product engineering space. Pandemic really hit hard on all of us. Guests were not reluctant to step into the stores and they was expecting more of a touchless experience. Business wanted to kind of provide a capability in our drive-up pickup where they wanted to give a Starbucks drink as an offering to the guest when they walk into our area for the pickup. Now we looked at it. This functionality looks simple, but then the complexity it involves is we have to get these capabilities run across 2000 stores in a real quick time. So how exactly we achieve them? With the help of this platform tenant construct, we clearly see that it's end of the day the capability which is nothing but business has to provide that Starbucks drink for the guest. So only the tenant layer undergo a change where they go and start providing these Starbucks drinks as an option for the guests to choose. And once guests choose those options, the platform component takes care of ensuring the entire smoothless checkout process. So that way we could able to bring in that agility to our business using this platform tenant construct. So here is a quick view of how exactly the commerce platform and the tenant constructs currently in our production. So we have these two boxes, carts and checkout. They are primarily the building blocks or the core components of our capability which we provide as a commerce. These commerce services talk to other core commerce services like item, price, promotion, etc. So that's where you see them on the left side of it. Towards the right side, you see these tenants like digital and stores, which primarily talks to these core services, which are carts and checkout, or driving the tenant business functionality specific to a channel. Site reliability engineering. This is the next pillar which we wanted to talk about, how we will achieve the stability. Intermittent failures in a large scale distributed systems is unavoidable. We all know that at given point in time, a particular service may go wrong and it will not function as expected. But the key question is systematically how exactly we could able to detect, isolate, and then recover from these issues. Site reliability engineering in our organization helps us bring in that cadence. We have thousands of microservice APIs running in the production as of today. Each of these microservice APIs are providing capabilities to the guest for different reasons. These are all built and deployed using different tools, technologies, frameworks and libraries. All these services are emitting these observability signals like traces, logs, events and metrics. But then what is the concern over here? The metrics which is being emitted or these observability signals which are being emitted are not in the consistency way. Let's look at it one example. If a guest do an add to cart in the digital, or let's say a guest does an add to cart in stores or scans an item in the stores, behind the scene add to cart API invokes minimum 15 microservices in our ecosystem to kind of give back that single response. Now all these services provides a different way of emitting their availability metrics. Now at that point in time, if I want to know what is an add to cart functionality available to the guest, I don't have a clear answer. Because each one of them within the service in that construct emitting their own way of saying I am available. So how do we resolve these consistency issues? SRE helps us in bringing in additional observability signals as well as the reliability principle as part of the SRE cadence. Now what exactly we do over here is we take care of two critical informations as part of the SRE. One is SLI, which is service level indicator, which kinds of gives across all these services what exactly the matrices we wanted to capture for. And then once we have these informations, we go ahead and have a pipeline to capture this and then convert it into a standard format. Now we have these SLI metrics for all the services. So then we could go ahead and build that SLO, which are nothing but the availability of these services over these SLI metrics. Now as part of the SRE standard, lot of organizations do different ways of defining their SLI metrics for their services. At Target, we do two critical matrices as part of our SLI services. One is timeliness, the other one is correctness. Timeliness we all know is nothing but how quickly the response is given back to the end user. Correctness is nothing but the successful response is sent back with an intent that it contains the required output. Now all our services within our target ecosystem will start emitting these two matrices, and once we have them converted into a standard format, we could go ahead and set a threshold against each of these matrices, and then alerts can be configured for any kind of breaches. So this way we could bring in that availability of a particular service by looking at the SLO metrics. So here is a quick snapshot of our add to cart SLO metrics. So if you clearly see it, most of the time we agree to say that SLOs should be 99.999, which is 5 nines. But on a certain given point in time, we have these SLOs which are emitting as 98.5. 6, 7, 8%. One thing to keep in mind, SLOs are data-driven approach. So there is nothing like a sentimental comes into our play saying that my service is available 99.999. These are data-driven approach where it accurately tells us that whether these services are available at what percentage. Along the lines of observability, we also consider reliability for our services. We are okay if the services at a given point in time is not available, but we take an approach of degradation performance over the disruption of our services. Now, as part of our SLO, SRE approach, we have these very 3 or 4 key SRE reliability principles. So, what exactly we follow the principles? We have this redundancy built in for our service, which means that whatever applications we deploy in a multiple location so that we don't get into this single point of failure. We also built in the fault systems. So any services which are getting disrupted at a given point in time, we automatically have a mechanism built in within our code to fall back to their available zones. For example, in stores, as I said, we have these mini cloud services which are up and running all the day. Now let's say that for a guest who does an add to cart, at a given point in time, one of the orchestrators realized that the service A, which is nothing but our price, is unavailable at that within the mini cloud. We have a mechanism where we automatically route to the available zone in the cloud. So we don't kind of get into a disruption of the service for the guest, but rather we kind of provide the service with a little bit of degradation. This way, we could ensure that our stabilities are kept in place for our services which are running in production. So we talked about two key pillars right now. One is for product engineering, how exactly it kinds of bring in our agility. And we talked about the SRE reliability, which is nothing but how exactly our stabilities are kept in place. Now the third one is performance engineering. Let's talk about what exactly we do in performance engineering. So we do let's say an add to cart functionality. Right? I keep taking that add to cart because that's a core services of our implementation. So let's say we take an add to cart service, and then behind the scene I already told that we have close to 15 odd different microservices which are getting invoked for our successful response to the guest. Now let's assume that I have a budget of not more than 80 to 100 milliseconds for my add to cart successful response, which means all these 15 odd services has to give back the response within 15 to 20 milliseconds. Maybe we would have used some kind of a good efficient way of running our program so that we could achieve parallelism, but still we need to ensure that these services has to be built in and respond back within 15 to 20 milliseconds. So this clearly says that performance is not something afterthought. So you have to build in that capability even during our design as well as during our development life cycle, so that we'll ensure that our services are performant as we expect to be there in the production. In Target, primarily we focus on two types of performance testing. One, where we do an end-to-end performance testing by the performance engineering team. The second one is in performance API test, which primarily does and run by the product engineering team. For the performance test which is run by our product engineering team, we do lot of things in the early stages of our build pipeline. So all our builds which goes through for any of the code change get tested through a performance test scripts. So we use Kaplan as an open source tool. So in our build pipelines, we have these plugged in. So every time a code is raised as a PR by the engineer, the performance test scripts are executed, and then we look at the report. Now any deviation in these will be looked by the engineer then and there, and then we stop getting these code into the production. So the PR will never get merged because the code is not up to the mark of the performance reports. We also do a synthetic test in production where we run constantly our performance APIs in production. So we look at it, the metrics coming out for every 10 or 15 minutes, and any sort of deviation from our agreed SLOs, we kind of alert to the systems, and the engineers will look at that issue upfront before even the guest gets to know. End-to-end performance testing is something which is done outside of our product engineering team. So the product engineering team only takes care of all these build pipelines and the production, running a production synthetic test. The performance engineering team primarily involves in running our applications end-to-end as a capability. They don't look for an part, or they don't look for a checkout or a guest signing profiles like that. So they do an end-to-end test, like how a guest will repeat that in the production. The guest walks into the tour site and then they do the look at the items, they'll see the PDP page, they'll add an item to the cart, and then they do all these transactions. So these kind of end-to-end scenarios is mimicked by our performance engineering team. They don't go by some random workload models. We typically use our actual production environment to determine what exactly are guest behavior patterns. So we use some of our previous years' stats and look at those and then kind of build in that workload model, keeping that performance scripts in place. So once we done that, we are sure that the performance, when we go for a days like a scalability day or an LTO day, we kind of meet the SLAs because we know that we have tested it enough in the production for that. And for that kind of a pattern which the guests typically come and do the shopping with Target. We also don't wait for any of these deal days or holiday seasons to kind of run our performance test against our API. We constantly do these tests on a regular basis in the production and ensure that the immediate feedback is provided to the engineering team for any kind of anomalies in the deviation of their API services. Last pillar to our discussion for today, platform engineering. Few years back, like as a product engineer, if the engineer wants to kind of look at it how they want to build a simple RESTful API service in Target, it used to take a lot of time for them to complete the process. While they will take care of running the entire functionality, they also need to take care of a lot of things. Things like persistence, things like building that capability of metrics, logging, and like authentication mechanisms, as well as things like failures or rate limiting, etc. It used to take at least 30 to 35% of our product engineering team's bandwidth to provide these capabilities. They don't focus on just building their core functionalities. They need to ensure all these things are taken care while they are building their API. Now at Target, we realize that there are multiple product teams which are building all these things same and again. So it's kind of a repetitive for our individual product teams doing these things again and again. And again, there is no standards which each of these teams would have followed. Over the last few years, we evolved ourselves by bringing in this concept called platform engineering. So what exactly we mean by that? As part of the platform engineering, the product engineering team responsibility is only in the top of the lane. They only worry about how exactly the functionality has to be built. They don't care about where exactly their code is getting deployed. They don't worry about how do I stitch my metrics, how do I stitch my logs, how do I get all these things into my measurement pipelines. Everything is taken care by the platform engineering team as part of a platform as a service. We provide a lot of services like database as a service, messaging as a service, measurement as a service. So all these things gets abstracted from the product engineering teams. So the product engineering teams time and value is in building the core business capabilities. Rest assure is taken care by the platform engineering team. So we have a special kind of platform as a service capability within Target. We call them as TAP, which is Target Application Platform. So what exactly it does is what I mentioned above. So as part of our code, which we get it deployed into the production, the end user, the business, the product engineer has to worry about in the central of the box. So he or she need not worry about how exactly the code is getting deployed. What happens to their metrics? How do they plug in the load balancing capability within the entire instances of the cluster? They don't have to worry about any of these authentication mechanisms. Everything is abstracted out from the product engineers and is provided by the platform as a service. Platform as a service also cater to a lot of other services like running it in a different clouds. Now, infrastructure as a service has provided that capability where even the platform as services can kind of run the services currently in a cloud like Google today. And tomorrow, if they wanted to run it in Azure, they could just quickly go ahead and switch over there. We don't have to say that, yeah, we need to build this capability to cater to this. So the infrastructure as a service layer provides that abstraction for platform as a service so that they could go ahead and build these services in any cloud providers instantaneously. So we adapt certain key principles as part of our platform engineering. The key principles are self-services, where the engineer has to get some services to be up and running for them. Let's say they wanted to build an application and they want to immediately need a Cassandra nodes. So they don't have to worry about how do I spin up these Cassandra nodes for my application to run. We just have them to provide a self-service and they request a self-service, and within a few seconds you get an information about where exactly they can go and use these Cassandra nodes. The artifacts with the guest, the business is running it, so it can go ahead and sit it in any cloud region. So the developer had no clue around where exactly their artifacts are getting deployed, and they don't have to worry about today I am running this application in cloud like GCP. Will I need to do anything for that to specially cater for my private cloud? No, you don't have to do that. It's completely immutable. So you take the artifact, today I can go and deploy in Google Cloud, and the same artifact can be go ahead and deploy in our private cloud. That's exactly what we do for commerce services. So we have these services running in Google Cloud for digital scenarios, and for our stores, we have our own private cloud. So we can go ahead and deploy the same artifact which comes out from the development process, so that they can go ahead and deploy it wherever we want to do it. We also provide a channel Google Cloud agnostic providers. So as I mentioned, as part of our IaaS service, which is infrastructure as a service, they provide these capabilities where you could go ahead and use whatever cloud provider you want. So you get a plugin over there, so that like you could go ahead and build them and then get it deployed in any cloud without any changes to your artifacts. So we talked about these four key different pillars: product engineering, how it kinds of brings in the agility to our services; performance engineering, how it kinds of build in the scalability; and then SRE engineering, how it can help us bring in the stability. Now, if you look at it, all these pillars executed in a combination of all these in an enterprises, it provides a flywheel effect to the enterprises, so that they can go ahead and leverage these capabilities as is, and the business can run smoothly without any issue. Thank you for the session.